This example is taken from the Signals and Systems textbook, and its result is quite important. In this video, we are going to solve it in greater detail so that we can review some of the concepts we learned earlier and also see how to obtain its Z transform. In the previous video, whose link appears above, we defined the Z transform and show that it can be written as the summation from negative infinity to positive infinity xn z to the power minus n. Using this definition, let's find the Z transform of the given signal. Substituting the signal into the definition, we obtain the summation from minus infinity to positive infinity minus a to the power n u minus n minus 1 multiplied z to the power minus n. Our first task is to determine the behavior of u minus n minus 1. As you know, the unit step function is equal to 1 only when its argument is greater than or equal to 0. Therefore, minus n minus 1 must be greater than or equal to 0. Solving this inequality gives n less than or equal to minus 1. This means that u minus n minus 1 is equal to 1 for n less than or equal to minus 1. And it's equal to 0 everywhere else. If we sketch this signal, it has a value of 1 at minus 1, minus 2, minus 3, while it is 0 for all values greater than minus 1. Since the unit step function is 0 outside this interval, we no longer need to sum from minus infinity to positive infinity. Instead, the summation becomes from minus infinity to minus 1. Also, because the unit step function is equal to 1 over this interval, we can remove it from the equation. Taking the minus sign outside the summation, the expression becomes minus times the summation from minus infinity to minus 1 a to the power n z to the power minus n. Now let's make a change of variable, replace n with minus n. After changing the summation limits accordingly, the expression becomes minus the summation from 1 to positive infinity a to power minus n z to power n. Since both terms have the same exponent, we combine their bases. Therefore, the expression becomes minus the summation from 1 to positive infinity a to power minus 1 multiplied by z all raised to the power n. Now let's simplify this summation. Recall the geometric series formula that we introduced in the previous Z transform lesson. The summation from 0 to positive infinity of b to the power n is equal to 1 divided by 1 minus b, provided that the magnitude of b is less than 1. Our summation starts from 1 instead of 0. To use the geometric series formula, we first add the term corresponding to n equals 0, and then subtract the same terms so that the expression remains unchanged. When n equals 0, the expression a to the power minus 1 times z all raised to the power 0 is equal to 1. Taking the minus sign into account, this contributes minus 1. Therefore, we compensate for it by adding 1 outside the summation. Now the summation starts from 0 and we can directly apply the geometric series formula. The convergence condition is the magnitude of a to the power minus 1, z must be less than 1. This is equivalent to saying the magnitude of z must be less than the magnitude of a. This condition is called the region of convergence, or simply ROC. If this condition is not satisfied, the infinite series doesn't converge and the Z transform doesn't exist. Now let's illustrate the ROC on the Z plane. Suppose this point represents A. Draw a circle centered at the region with radius the magnitude of A. Since the ROC consists of all points whose distance from the origin is less than the magnitude of A, the ROC is the entire interior of this circle. Now let's simplify the Z transform. Taking a common denominator, we obtain minus a to the power minus 1 multiplied by z divided by 1 minus a to the power minus 1 multiplied by z. Finally, multiply both the numerator and denominator by minus a. The expression simplifies to z divided by z minus a. Now let's identify the pole and the zero. As we explained in the previous lesson, the values of z that make xz equal to 0 are called the zeros. If we substitute z equals 0, the numerator becomes 0. Therefore, there is 1 0 at the origin. On the z-plane, zeros are represented by circles. The values of z that make xz approach infinity are called the poles. Here, the denominator becomes 0 when z equals a. Therefore, there is one pole at z equals a. Poles are represented by crosses on the z-plane. You may notice that we previously solved another example with the signal a to the power n multiplied by un. Its z transform was also z divided by z minus a. So how can we distinguish between these two different signals if they have the same algebraic expression? The answer is simple. We must always pay attention to ROC. For the signal a to power n multiplied by un, ROC is the magnitude of z greater than the magnitude of a. However, for the signal we solved in this example, ROC is the magnitude of z less than the magnitude of a. Therefore, in the Z transform, the ROC is just as important as the transform itself. Without the region of convergence, the signal can't be uniquely identified. We will continue solving more examples like this in the upcoming videos. If you found this tutorial helpful, please like the video and subscribe to the channel. If you have any question, feel free to contact me through my Telegram ID or email address provided in the video description.